Good evening. Undoubtedly, the most exciting astronomical event in recent years has been the outburst of a supernova in the Large Cloud of Magellan. A supernova is a colossal outburst, thousands of millions of times more powerful than the Sun, involving the total destruction of a star. But they're rather rare, and the last one seen in our galaxy was way back in 1604, which of course was before the invention of the telescope. And astronomers would very much like the chance to have a look at a fairly nearby supernova with modern type equipment. Well, we haven't had that. We have had the next best thing, because in the Large Magellanic Cloud, a supernova has appeared. The Large Cloud is a separate galaxy, too far south to be seen from here, about 170,000 light years away. And the supernova appeared here, and it was very conspicuous indeed. It was brighter than all the other stars in the galaxy put together. And I went down to have a brief look at it from South Africa, and this was a picture that I took with a handheld camera and an exposure of 40 seconds. And the supernova is the brightest thing you can see on that picture. It's a great pity that it was too far south to be seen from here, but obviously all the observatories in the southern hemisphere have been paying great attention to it. And the lead has been taken by the Anglo-Australian Observatory in New South Wales, where the main telescope is the 158-inch reflector. Certainly, there are many questions to be answered. And at this stage, I'm delighted to introduce once again one of our most regular and welcome visitors, Dr. Paul Murdin of the Royal Greenwich Observatory. Paul, what kind of questions do you think are going to be set by this supernova?
Well, the main questions are going to be studied and answered, I think, through optical spectroscopy. And straight away, the supernova presents a big problem to a big telescope like the Anglo-Australian telescope. A big telescope like this is set up to study faint stars and quasars, distant things on the edge of the universe. And the supernova, in fact, made it into the top 100 brightest stars almost. So it was necessary to construct special equipment in order to study the spectrum in the detail that it would deserve. In a conventional astronomical spectrograph, there's a diffraction grating like this, which generates the rainbow-like spectrum which the spectrograph records. You can see the spectrum here of the studio lights, in fact. This grating is something like 15 centimeters across, and it would fit into a conventional spectrograph on a telescope. But for a really detailed look at the spectrum, you need a big grating this size or more in a big spectrograph. The small grating fits into a spectrograph which hangs on the back of the telescope. And the big grating, it's necessary to house in a spectrograph which is the size of a room. And you need, in addition, a collimator lens which will take the diverging beam from the telescope, render it parallel and pass it into the grating, and a big camera lens to converge that light onto a single color rather than the rainbow-like spread of colors, the whole rainbow that the small spectrograph sees.
What do you think you're going to learn about the supernova from the results taken with this grating?
One of the things you can have a look at is the expansion speed of the supernova. That comes to us through a phenomenon called the P Cygni profile of the spectral lines that spectrographs record. P Cygni is a variable star that has a fundamental structure much like the supernova. There's a central body surrounded by an expanding atmosphere. And the two components that these two objects would give us if they were separated are a continuum covering the whole rainbow-like spectrum with an emission line superimposed on top. In fact, the central body is inside the atmosphere, and this produces interesting geometrical effects. First of all, there's a part of the atmosphere silhouetted against the central body, and this produces an absorption line. The absorption line is Doppler shifted off to one side because that part of the atmosphere is approaching us. Secondly, there's a piece of the atmosphere which is in shadow behind the body, and that part of the emission line that would produce is missing from the spectrum entirely. The net result is to have an S-shaped profile called the P Cygni profile, and the distance between the absorption line and the emission line tells us the expansion speed of the supernova.
Well, in that diagram, we've shown the supernova as round. But, Paul, is it round?
Astronomers are simple-minded people, and they'd like to start with the simple analogy to see if they understand that. But there's no reason why the supernova should be round. We know of many explosions in terrestrial experience that aren't spherically symmetrical, mushroom-shaped clouds and so on. But if we go back to our diagram of the atmosphere of the supernova surrounding the central body, the light that comes from the atmosphere could be polarized, for example, circumferentially, so that the polarization vectors are oriented around the supernova. From our distant view of this supernova, 200,000 light years away, we get a blurry view of the whole image, and the up and down polarization vectors cancel out the sideways polarization vectors. That is, if the supernova is round. If it's elliptical, then the polarization vectors could run circumferentially as before, but there's an excess of polarization vectors along the long axis, and when we see the blurry view, there may be more up and down polarization vectors left than are cancelled out by the sideways ones. There's a net polarization. And because the polarization is connected to the atmosphere, and the atmosphere is connected through the P Cygni profile to a particular wavelength, then if the supernova is not round, we can see a change of polarization with wavelength that would tell us that it's not round, in fact.
Well, so far as the astronomers are concerned, the Earth's atmosphere is an unmitigated nuisance. It's dirty and it's unsteady. But nowadays, of course, there are ways of getting around this, and I'm thinking of spectral interferometry.
Yes. Supposing the telescope is like this camera, and supposing the atmosphere is like this multi-image filter which fits over the top of it. This filter has got different prisms of glass which correspond to different bubbles of different refractive index in the atmosphere. We've got a similar system attached to a television camera in the studio which is looking at a model of a double star. The view that the television camera sees of the double star is multi-image. There are several images of the double star recorded at any one time. And the shifting of the atmosphere, the way the bubbles are blown around in the wind, corresponds to the rotating of this multi-image filter over the television camera lens. Now, if you recorded images like this with a video recorder, say one image every few thousandths of a second, you could freeze the motion of the atmosphere. You could then take these images back home to your computer system and analyze them in the computer. You could slide individual images from side to side and up and down and look at the correlation of one image with another. If you do the sliding in the right direction, then the images correlate and the images get sharper and brighter, and you can see more detail in the image.
So there are many techniques and many questions to be answered. Recently, there was a major conference held at the Royal Observatory, Edinburgh, and one of the astronomers there was Dr. Russell Cannon, the director at the Anglo-Australian Observatory. And I asked him how they coped with the sudden appearance of the supernova.
The big problem, of course, is that the Anglo-Australian telescope is used by a lot of astronomers from Britain and from Australia, and that they compete very hard to get their precious time on the telescope, 1 or 2 nights each, and they plan this months in advance. And so these people were coming out ready to do their special astronomical projects. And although everybody agreed that this supernova was so very important that clearly we ought to devote a lot of time to it, everybody would rather have it somebody else who was giving up the time to do it. So what we agreed straight away was that it would be worthwhile having 10% of 1 hour of the time each night should be spent on the supernova with whatever equipment happened to be on the telescope and whoever was using it. And that the data that we got that way would go into a common database for the use by all astronomers and not be the personal property of the people who happen to be collecting the data.
Presumably, you had to build some new equipment especially for the supernova.
Well, that's right. We had plenty existing equipment to do many kinds of observation, but this was such a good opportunity to do something special with such a bright source and so far away and so, as you say, unusual, first one for 300 years, that we decided that it was worthwhile to invest a fair bit of effort into building a special spectrograph to get spectra much higher dispersion, much more magnified than the sort of spectra that we normally take of faint stars and galaxies. And to do that, we wanted to get about 10 times higher magnification than we could do with our existing equipment. And we're very fortunate that Peter Gillingham, the chief engineer at the observatory who's in charge of the telescope, realized that he could put together a suitable spectrograph out of essentially bits and pieces that we borrowed from places all around the world. We got a grating from a team in University of London who were building a new spectrograph for us, but which won't be ready till after the supernova has faded, unfortunately. We made a lens. One of our night assistants is a keen amateur who grinds his own mirrors, And he had all the right equipment, and we found a glass blank, and he was able to make a new lens to focus the light in the spectrograph. And we borrowed other bits and pieces and put this thing together on wooden benches. So it's a highly improbable-looking string and sealing wax piece of equipment.
Certainly works, though. What have the spectra told you so far?
Well, we've done several kinds of spectra. The ones of the supernova itself have been using our ordinary standard spectrographs. And the sort of things it's shown us is that the supernova, of course, is expanding very fast after the explosion. And you see that, you recognize that from what we call the P Cygni profile, which is named after a star with an expanding shell around it. And in the supernova, what we saw were P Cygni profiles. These are a sort of S-shaped profile with absorption line and an emission line next to each other, but enormously broad, and indicating that there were enormously high velocities, 30,000 kilometers per second, when the supernova first went off. And then at a later date, a few weeks later, the same shape of profile came, but much narrower, which meant that what had happened was the fast expanding material had moved out and become transparent, and we were seeing deeper into the supernova, seeing the stuff coming more slowly.
Quite apart from the supernova itself, it's telling you a great deal about the interstellar medium, I imagine.
That's right. Simply because it's very bright and very far away, it gives us, if you like, a lighthouse, a background light source to use to probe the material in between us and the supernova. Because the light, as it comes towards us, is passing through clouds of dust and gas in the Large Magellanic Cloud at the far end, in our galaxy, and anything that happens to be in between. And that gives us characteristic lines in the spectrum of the supernova, little dips where the atoms of calcium, sodium, and so on are absorbing the light from the supernova. And to do this properly, you need to get a very highly magnified spectrum. And this is what we did with this new spectrograph. And what we discovered from that, the remarkable result, was that these clouds of gas in space are much cooler and moving much more slowly than anybody expected. And we measure that because the lines are extremely sharp, and we can see detail in the lines in the spectrum, which we never expected and which had never been seen before in these kinds of clouds.
What about the supernova itself? Is it in fact round, or isn't it?
Well, the theoreticians would like it to be round because they're having a hard time modelling it even as a round explosion. It's a very complicated system to model. But in practice, we've got evidence that it's not round, coming in two ways, and one of these is from polarization. The light from the supernova is polarized. And that's not a surprise because you get some polarization just from the light coming through space towards us. Light from many of the stars becomes polarized because it's traveling through dust, being reflected off dust on the way. But the thing that tells us that the supernova is not round is that when you look at the polarization, instead of a straight, flat line, a straight, level polarization, not changing at all, what happens with the supernova is it turns out the polarization changes dramatically with wavelength. As you go through these P Cygni profile lines in the spectrum, instead of the polarization staying constant all the way through, it goes up to peaks as you go through the line. And that tells us, if nothing else, that the thing cannot be simply spherically symmetrical or circularly symmetrical.
Why do you think it isn't round?
That's a difficult question. It's very hard to see. One possibility is that the star didn't explode completely symmetrically if it was perhaps rotating or had a magnetic field which would make it expand more easily in one direction than in others. Or it may be that it's in blowing itself apart. It simply didn't blow off as a nice uniform spherical shell, but it fragmented into pieces. Or it may be that it is round, but that what's happened is that we're seeing some of the light reflected off blobs of dust and gas which were near the supernova before it exploded. And so the light that we see isn't just the supernova light, but it's a mixture of light from these other objects, and the total effect is it isn't simply a round, smooth thing on the sky.
What about the spectral results?
Well, that's the other indication that things not round. In fact, right at the start, when it went off, we had a team from Imperial College in London who wanted to come and make speckle observations. Speckle's a technique, as you know, to make images of things much smaller and sharper than the normal image that you get from the atmospheric seeing. And their initial objective was to measure the diameter of the supernova as expanded. And they thought, well, great, this is going to be the first chance. But this is a funny supernova. And the thing didn't get as big as it was supposed to. In fact, it stayed much smaller than most supernovae have. And so they knew, even when they arrived in Australia, that it was almost certainly too small to get a diameter measurement. But they continued because you never know what you're going to find. And what they found was that, in fact, the thing isn't round, and that they found evidence of a little mystery blob, mystery object, off to one side of the supernova, but only a small fraction of a second of arc away. So this little object sitting there.
Any idea what it is?
Well, the first thoughts were that it might be a cloud of gas or dust which had been illuminated by the light from the supernova explosion. We could tell straight away that it's not stuff from the supernova itself, because it's far enough away, even though it's very close, that even material moving would have to move almost at the speed of light to have got there. So clearly it can't be material. We also know that it must be something to do with the supernova, because although it's much fainter than the supernova, it's still much brighter than anything else that was there before the supernova went off. And so maybe it's a cloud of gas which got illuminated by the initial explosion, and that's what we're seeing, sort of reflection.
I'm intrigued by this companion object. Why mystery spot?
Well, I scarcely need to explain the word mystery, but if you take the scientific data of the kind which Russell showed us in his interview and construct a computer image from that, then the object, the mystery object, shows up as a spot off to the side of the image of the supernova.
Well, it's quite unmistakable. What do you think it is?
I'll tell you what Martin Rees of the Institute of Astronomy at Cambridge thinks it might be. Martin makes the guess that the supernova occurred in a binary star system, that it had a companion. The waves of ejecta that were flung out from the supernova collided with the companion, and as they passed it, the companion punched a hole in the shell as it expanded outwards. The companion moved off to one side and uncorked the hole so that all of the excited material which is inside the supernova can squirt out in a jet which can move nearly as fast as the speed of light. This jet passed across space and found a cloud which was nearby, and the place where the jet hit the cloud is the place where the mystery spot appeared. That's the theory of Martin Rees at Cambridge.
Well, I suppose we will find out. Paul, I wonder what the end product of this supernova is going to be. Pulsar, black hole, or what?
I don't think anybody really knows yet. I would like myself for it to be a black hole, and I think it might be a black hole because there appear to have been two neutrino bursts from the supernova, one of which represented the formation of a neutron star, and the second one represented the collapse of the neutron star to be a black hole. But we won't know for sure until all the debris from the supernova is cleared enough to see what's inside, and I'm hoping that when that does, we'll see a black hole in the middle.
Well, it's certainly an exciting event. After all, this is the brightest supernova since 1604, and I just wonder when they're going to get the next one.
Well, it could be tomorrow. When you and I saw Halley's Comet recently, we knew that in our lifetime we wouldn't be able to see it again. Halley's Comet is periodic and won't come back for 76 years. But supernovae aren't like that. The appearance of one supernova is not correlated with the appearance of the previous one. In fact, the light from 5,000 galactic supernovae is traveling across the galaxy on its way to us now. It hasn't reached us yet. There are a few hundred supernovae have occurred in the Large Magellanic Cloud, and we haven't seen them yet either. We could see the next naked eye supernova tonight. We should get out of the studio and have a look, perhaps.
Well, let's hope we do. It must be great to see a supernova in our own galaxy, possibly shining more brightly than Venus does to us. But meanwhile, Paul, we're learning a great deal from this one in the Large Magellanic Cloud. And when we have more news, we'll come back and tell you. So from Paul and myself, good night.